Hey everyone, welcome back. We're doing a deep dive today on some cool physics
Good.
stuff,
Oh, yeah.
inspired by the Open Educational Resources Open Source Physics at Singapore website
Okay.
that you
Yeah.
sent us. And so get this, we're talking about using electric and magnetic fields to isolate particles,
Wow.
moving at a specific velocity. It's called the velocity selector.
Okay.
And trust me, it's way cooler than it sounds.
So what's fascinating about this is that, we're talking about controlling the motion of these really tiny particles
Right.
by manipulating these fundamental forces. And so,
Yeah?
it's this really delicate balance, but it opens up so many different possibilities.
Okay, I'm already intrigued.
Yeah.
So walk me through this. How do these velocity selectors actually work? The website mentions an interactive simulation, which I'm guessing will come in handy.
Absolutely. So imagine a charged particle, cruising into a region where electric and magnetic fields are perpendicular to each other.
Hmm.
What we call crossed fields.
Cross fields, now you're just showing off.
No, but it is an important term. It means the fields are oriented at a right angle to each other, which is really crucial for the velocity selector to function.
Okay.
Now, the electric field, let's visualize that as red arrow,
Okay.
exerts a force on the particle in one direction.
Okay.
Meanwhile, the magnetic field, pictured as an orange arrow, exerts a force in the opposite direction.
Ah, so it's like a tiny particle tug of war.
Exactly.
But how does this isolate particles with a specific velocity?
It's all about achieving this perfect balance. The electric force, represented by a green arrow in the simulation, depends on the charge of the particle and the strength of the electric field.
Okay.
The equation for this is F equals QE, where Q is the charge and E is the electric field strength.
So stronger field, stronger force makes sense.
Yeah.
But didn't you say the magnetic field also exerts a force?
Right, and this is where the velocity dependence comes in.
Okay.
The magnetic force, shown as a cyan arrow, is calculated using the equation F equals QVB, where V is the velocity of the particle, and B is the magnetic field strength.
Hold on. So if V, the velocity, is 0, then the magnetic force is also 0. Is that right?
Precisely. And that's key to the velocity selector's function. Only particles with a specific velocity will experience equal and opposite electric and magnetic forces, allowing them to pass straight through the selector undeflected.
Wait, so those particles have a specific velocity to achieve this balance?
Exactly. By adjusting the strengths of the electric and magnetic fields, we can select for particles with different velocities. Think of it like fine-tuning a filter
Right.
to let only certain particles through.
Okay, so the particles moving faster or slower than this specific velocity would experience an unbalanced force and get deflected.
Right.
So it's more like a cosmic bouncer booting out anyone who doesn't meet the velocity requirement.
I like that.
That's pretty amazing, isn't it? We're controlling particle traffic on a microscopic level.
It is quite remarkable, and this principle has some pretty powerful applications.
Yeah.
For instance, mass spectrometers use this very concept.
Mass spectrometers. I've heard that term thrown around, but honestly, I'm a bit fuzzy on the details.
They're incredible instruments used to analyze the composition of substances. Essentially, they separate ions based on their mass-to-charge ratio, giving us a sort of molecular fingerprint.
Okay, back up a sec. Mass-to-charge ratio. Break that down for me.
Think of it this way. Each atom or molecule can have a different mass and charge. The mass-to-charge ratio is simply the mass of the ion divided by its charge. This ratio is unique for each type of ion, allowing us to identify them.
Ah, so it's like a unique identifier for each ion.
Yeah.
But how does the velocity selector fit into all of this?
Well, in mass spectrometer, ions are first accelerated by an electric field, but they don't all accelerate to the same speed
Right.
due to their varying mass-to-charge ratios.
Ah, I see where you're going with this. So you use a velocity selector to ensure only ions with a specific velocity enter the next stage of the mass spectrometer.
Exactly. This ensures we're comparing apples to apples, so to speak. Only ions with the selected velocity pass through to the next stage, where they are further separated based on their mass-to-charge ratio, ultimately allowing us to identify and quantify the different components of the sample.
So we're talking about sorting ions with incredible precision based on their mass and charge just by manipulating electric and magnetic fields. I'm starting to understand why you find this so fascinating.
And this is just the tip of the iceberg. Velocity selectors and their applications are far more widespread than you might imagine. They're used in everything from particle accelerators used in cutting-edge physics research
Wow.
to medical imaging devices that allow us to peer inside the human body.
Wow. From analyzing the composition of matter to medical breakthroughs, It seems like understanding the interplay between charged particles and electromagnetic fields is fundamental to so many technologies we take for granted.
It's true. And what's really exciting is that we're still discovering new ways to harness these forces. For example, researchers are exploring the use of magnetic fields for levitating objects, potentially leading to frictionless transportation systems. Imagine trains gliding effortlessly above the tracks with no physical contact.
Okay, now that sounds straight out of science fiction.
Yeah,
But if we can manipulate ions on a microscopic level,
right.
why not apply those principles to larger objects?
Mm.
It's mind-boggling to consider the possibilities.
And that's just the beauty of science, isn't it? There's always more to learn, more to explore. What we know today is just a stepping stone to the incredible advancements of tomorrow.
Totally. You know, it's funny. I remember reading science fiction books as a kid where they talked about levitating vehicles and thought, that's cool, but it'll never happen.
Right.
Now here we are talking about manipulating magnetic fields to achieve just that.
Yeah.
It makes you wonder what other seemingly impossible feats might be within our grasp.
Well, it's a testament to the power of scientific inquiry.
Yeah.
What was once pure fantasy can become reality through, understanding and harnessing the laws of physics.
Right.
And who knows, maybe someday those levitating trains will be commonplace.
Yeah. But let's not get ahead of ourselves. We were
Uh-oh.
talking about the incredible precision of mass spectrometers.
Yeah.
Are there any limitations to this technology? I mean, can we analyze any substance no matter how complex?
That's a great question. While mass spectrometry is an incredibly powerful tool, it does have its limitations.
Okay.
For example, some molecules are very fragile and can break apart during the ionization process, making analysis tricky. And the accuracy of the measurements depends on a variety of factors, including the quality of the instrument and the expertise of the operator.
So it's not quite a magic bullet,
Yeah.
but still the ability to identify and quantify the components of a sample at such a granular level is remarkable.
Absolutely. And the applications extend far beyond simple analysis.
Oh.
For instance, mass spectrometry is playing a crucial role in fields like proteomics, the study of proteins.
Okay.
By analyzing the proteins present in a sample, researchers can gain insights into disease processes, develop new diagnostic tools, and even design targeted therapies.
Wow, so we're talking about a technology that can help us understand the building blocks of life itself.
Yeah.
That's incredible. But I have to admit, I'm still struggling to grasp the concept of levitating trains. Is that really feasible, or is it more of a theoretical possibility?
Well, the principles are sound. We know that magnets can repel each other, and we've already achieved magnetic levitation with smaller objects.
Right.
Scaling that up to the size of a train presents some engineering challenges,
Okay.
but it's not beyond the realm of possibility.
I guess the real question is it practical? I mean, wouldn't the energy requirements for levitating a massive train be astronomical? And how would you control its movement?
Those are valid concerns, and they're precisely the kinds of questions engineers are grappling with as they explore this technology.
Right.
One promising approach involves using superconducting magnets, which can generate much stronger magnetic fields while consuming less energy.
Okay.
As for control, that would likely involve a combination of magnetic fields and other guidance systems.
I'm picturing a future where trains silently glide above the tracks at incredible speeds, all powered by carefully orchestrated magnetic fields. It's a captivating vision. But I can't help but wonder about the potential downsides. What about the safety implications of such powerful magnetic fields? And what about the environmental impact of manufacturing and deploying these systems?
You bring up important points. Any new technology comes with potential risks and benefits, and it's crucial to carefully assess those before widespread adoption. The safety of passengers and the environment would be paramount considerations in any large-scale implementation of magnetic levitation technology.
Speaking of pushing the boundaries of technology, you mentioned earlier that velocity selectors are used in particle accelerators. Now, those are some seriously impressive machines designed to accelerate particles to incredible speeds.
Yeah.
Can you tell me more about how velocity selectors play a role in that process?
Of course, particle accelerators use electric fields to accelerate charged particles to high speeds. However, just like with the ions in a mass spectrometer, these particles don't all accelerate uniformly.
Right.
That's where velocity selectors come in. They're used to filter out particles that aren't moving at the desired velocity, ensuring a more focused and controlled beam.
So it's all about fine-tuning the beam,
Yeah.
making sure all the particles are moving in sync. But why is that so important? What's the end goal of accelerating these particles to such high speeds?
Particle accelerators are used for a wide range of scientific research.
Uh-huh.
By smashing particles together at high energies, physicists can recreate the conditions that existed in the early universe, providing insights into the fundamental building blocks of matter and the forces that govern them.
It's like recreating the Big Bang in a lab.
In a sense, yes. Particle accelerators are like giant microscopes, allowing us to probe the inner workings of the universe at the most fundamental level, and velocity selectors play a key role in making those experiments possible.
It's incredible to think that a seemingly simple concept, like a velocity selector based on the interplay of electric and magnetic fields, can have such far-reaching implications. From analyzing the composition of matter to unlocking the secrets of the universe, these devices are truly at the forefront of scientific exploration.
And it doesn't stop there. Researchers are exploring the use of velocity selectors in various other fields, including isotope separation, nuclear medicine, and even space exploration. The possibilities are truly limitless.
As we delve deeper into this topic, it's becoming clear that velocity selectors are not just scientific curiosities. They're fundamental tools that are shaping our understanding of the world and driving innovation across a wide range of disciplines. And what's even more exciting is that we're only just beginning to scratch the surface of their potential. But I have to ask, with all this talk about manipulating charged particles, is there any way to apply these principles to something larger, something more tangible? Could we, for example, use electric and magnetic fields to manipulate objects at the macroscopic level?
That's an intriguing question, and it's one that scientists and engineers are actively exploring. You see, while the effects of electric and magnetic fields are most pronounced at the microscopic level, they do exist at larger scales as well.
Right,
Think about the Earth's magnetic field, for instance.
right.
It's a massive field that extends far out into space, and it has a profound influence on our planet.
So if we can harness those forces on a larger scale, what could be possible? I mean, we've already talked about levitating trains, but are there other applications we haven't even considered yet?
Absolutely. Imagine, for example, using carefully controlled magnetic fields to manipulate objects in manufacturing, creating a sort of frictionless factory where parts move effortlessly through the production process. Or perhaps we could use magnetic fields to create new forms of energy storage or even develop entirely new modes of transportation.
It's mind-boggling to think about the possibilities, but
Yeah.
I suppose that's the beauty of science, isn't it? It's about constantly pushing the boundaries of what we know and exploring the unknown. And who knows, maybe someday we'll be using electric and magnetic fields to do things we can't even imagine today. But for now, let's bring our focus back to the microscopic world and delve a little deeper into the fascinating world of velocity selectors. You mentioned earlier that they're used in isotope separation. Now, I know that isotopes are atoms of the same element that have different numbers of neutrons, but can you elaborate on how velocity selectors play a role in separating them?
Certainly, isotope separation is a crucial process in various fields, from nuclear power to medical research.
Okay.
One way to separate isotopes is to use a device called a calitron, which employs a velocity selector to filter out ions of a specific isotope based on their mass-to-charge ratio.
So it's like a high-tech sorting machine for atoms.
Essentially, yes.
Yeah.
The calitron creates a beam of ionized isotopes, which are then passed through a velocity selector. By adjusting the strengths of the electric and magnetic fields, only ions of the desired isotope will pass through undeflected while others are diverted away.
It's amazing how such a seemingly simple concept can be applied in such sophisticated ways. And speaking of sophisticated applications, you also mentioned nuclear medicine. I know that radioactive isotopes are used in various medical treatments and diagnostic procedures. So how do velocity selectors fit into that picture?
Well, in some cases, it's essential to isolate specific radioactive isotopes for medical use.
Okay.
For example, in positron emission tomography, or PET, scanning a radioactive isotope is attached to a tracer molecule that's injected into the patient. The tracer accumulates in specific tissues or organs, and the emitted positrons are detected by a scanner, allowing doctors to visualize and diagnose various conditions.
So velocity selectors can help ensure that the radioactive isotopes used in these procedures are pure and free from contamination.
Exactly. By carefully selecting the desired isotope, doctors can minimize the radiation exposure to the patient while maximizing the diagnostic or therapeutic effectiveness of the procedure.
It's remarkable how something as seemingly esoteric as a velocity selector can have such profound implications for human health and well-being. But I'm curious, are there any limitations to the use of velocity selectors in these medical applications?
As with any technology, there are always challenges. For instance, the production of certain radioactive isotopes can be expensive and time-consuming, and the equipment used for isotope separation can be complex and require specialized expertise. However, the benefits of using pure isotopes in medical applications often outweigh these challenges.
It's clear that velocity selectors are playing an increasingly important role in various aspects of our lives, from fundamental scientific research to cutting-edge medical treatments.
Right.
And as our understanding of electromagnetism continues to grow, I'm sure we'll discover even more innovative ways to harness these forces for the benefit of humanity. But for now, let's shift our focus to the final frontier, space exploration. You mentioned that velocity selectors have applications in this realm as well. Can you elaborate on that?
Certainly, space is a harsh environment filled with charged particles from the sun and other cosmic sources.
Right.
These particles, known as cosmic rays, can pose a significant hazard to astronauts and sensitive equipment.
Yeah.
One way to mitigate this risk is to use magnetic fields to deflect these particles away from spacecraft and habitats.
Okay.
And guess what plays a crucial role in controlling these magnetic fields? You guessed it, velocity selectors.
So velocity selectors are like tiny guardians protecting our astronauts and spacecraft from the invisible dangers of space.
In a way, yes. They help create a sort of magnetic shield deflecting harmful cosmic rays and ensuring the safety of our spacefaring endeavors.
It's incredible to think that a concept born in the laboratory can have such profound implications for exploring the vastness of space. It really underscores the interconnectedness of science and the power of human ingenuity.
And it highlights the fact that we're still at the early stages of understanding and harnessing the full potential of electromagnetism.
Right.
Who knows what incredible discoveries and applications await us in the future?
Indeed. As we wrap up our exploration of velocity selectors, it's clear that these devices are much more than just scientific curiosities. They're powerful tools that are shaping our world in profound ways, from unlocking the secrets of the universe to protecting our astronauts in space. And as we continue to delve deeper into the mysteries of electromagnetism, I have no doubt that we'll discover even more innovative and transformative applications for these remarkable devices. As we wrap up our deep dive on velocity selectors, I'm really struck by how this seemingly simple concept has so many wide-ranging applications.
I agree. It's a real testament to the power of just like fundamental physics and how it underpins so much of our technology and understanding of the world.
And it all boils down to the interplay between electric and magnetic fields. Makes you wonder what other secrets of the universe might we unlock by further exploring and harnessing these forces.
It's a question that drives countless scientists and engineers around the world. The quest to understand and control electromagnetism has led to some of the most groundbreaking discoveries in human history, and there's no doubt that this field holds immense potential for future innovation.
So to bring it all back to you, what stands out to you as the most fascinating aspect of velocity selectors? What really sparked your curiosity as we delved into this topic?
For me, it's the sheer elegance of the concept. By carefully balancing these fundamental forces, we can achieve an incredible level of control over the motion of charged particles. And this control has opened up a world of possibilities, from analyzing the composition of matter to exploring the vastness of space.
I have to agree with you there. There's something profoundly satisfying about seeing how a simple principle rooted in basic physics can be applied in such diverse and ingenious ways.
And it speaks to the beauty of science itself. It's a process of constant discovery, of pushing the boundaries of knowledge and exploring the unknown. And who knows what amazing applications of velocity selectors we might uncover in the years to come.
Well, one thing's for sure, we've only just scratched the surface of this fascinating topic. But as we wrap up our deep dive, I want to leave you with a final thought to ponder. We've seen how velocity selectors can be used to isolate and manipulate charged particles. But what if we could apply those same principles to larger objects, even macroscopic ones? Could we create a world where we manipulate matter with the same precision and control that we currently manipulate atoms and molecules? It's a tantalizing thought, and one that might just inspire the next generation of scientists and engineers to unlock even more incredible possibilities. Thanks for joining us on this journey of discovery, and keep exploring the wonders of the universe.